In this series of lectures or videos, I'm going to go through quite quickly the 5 parts that are included in week 15. Okay, in week 15, we have gone through the 2 procedures for generating a fermentable type of solution. And then we have looked at how that fermented solution that contains ethanol can be extracted, how the ethanol can be extracted through the process called fractional distillation. And so in order to get an understanding of the fractional distillation, I put together this series of Word documents that kind of help to explain the process. And again, I'm going to go through this fairly quickly. And so in the first document, which is entitled An Introduction to Saturated Vapor Pressure, it discusses the pressure that exists above a liquid-vapor interface for a liquid. And so when one has a liquid that is confined and there is a surface associated with the liquid and the liquid is at a given temperature, what happens is there is an interaction that occurs wherein some of the liquid molecules have enough energy to actually escape into the vapor phase. Excuse me. Additionally, what happens is some of the molecules that are in the vapor phase can actually hit the interface and actually lose that energy and actually go back into the liquid phase. And so in a small region of the liquid near the surface, that's happening. Okay, and so if that liquid was in a closed container, what happens over time then is that the molecules that are released and the molecules that are reabsorbed reach an equilibrium. And so this is kind of what you see happening, is that some of the liquid molecules have enough energy to escape into the vapor phase, and some of the vapor molecules lose or hit the surface and lose the energy and become liquid. And so there is an equilibrium that is set up. So in this particular scenario then, what happens is at the temperature that this solution is at, there is a measurable pressure which corresponds to the energy of the vapor phase molecules above the surface. And that, if one was to measure that, that is referred to as the saturation vapor pressure. In thermodynamics, that's a very important concept for a pure substance. Based on the temperature of the substance, there is a unique vapor pressure associated with the pressure that would exist in a closed vessel at that particular equilibrium condition. How is that manifested? Well, what happens is, if we have a substance such as mercury, mercury is a pure substance, and at a given temperature, mercury has a vapor pressure associated with it. And in fact, if one was to take a column of mercury and have it filled up, this is a tube. If you turn that around and filled it up with mercury and then very quickly brought it into this pool of mercury, what would happen is the mercury would fall and under the presence of gravity, and what would originally happen then is that the original level might be here, but some of it then falls and is pushing down, and so it ends up being at this particular point here, the final position. Then what happens is, if one were to measure the pressure of the mercury above that thin layer of the interface, that would be the vapor pressure of the mercury at the temperature of the mercury. And if the original column height was 760 millimeters, and then we go to this location here where the new height is 630, the difference between those two then corresponds to the vapor pressure of the liquid mercury above. And so that 130 difference then is a high vapor pressure associated with the system. And so the thing that keep in mind is, for any pure substance, the saturation vapor pressure varies with respect to temperature. And we could plot that in kPa, which are the pressure units, the saturation vapor pressure for something like the pure substance of water, if we were to plot that against the temperature in Celsius, one would find that the dependency would look like this. Okay, at 100 degrees, we know that water boils at 100 degrees. Well, it just so happens that at 100 degrees, the saturation vapor pressure is equal to 100 kPa, or atmospheric pressure. And so that's why we see, and that's why we say that water boils. It goes between the liquid and the vapor phase whenever the pressure is equal to the atmospheric pressure. If we were to lower the temperature of the water then actually will boil at a lower pressure. Or saying it another way, if we were to lower the saturation vapor pressure of water, we could see that the temperature that the boiling process would occur would decrease. And so saturation vapor pressure and boiling point are directly related to each other. When we say something has a high saturation vapor point, that usually implies that it has a certain boiling point associated with it. And when it has a lower vapor pressure, it means it has a lower boiling point. And the relationship looks like this. The same thing can be said for saturation vapor pressures with solids and the concept of solids. But for right now, we're really only interested in boiling and condensation that occurs as a substance goes from the liquid to the vapor condition.